Okay, good morning. So I know that one part of chapter 1, which is related to the limit of the functions, is left, but let me try to do it a little bit differently from what I did so far. So I want to start with chapter 2, which is the notion of the derivative, and probably that is this one and the next one, which is related to the integrals, are the most important part of this course, and they will be continued in Math 4 as well. So what we learn here is actually very, very important if you are going to take Math 4 as well, because if you don't have good understanding here, and you forget things from here to, then you will be in trouble in Math 4. Before starting that, let me refresh your memory a little bit about what we will need from Math 1C. So let me just write a recap here. So, you know that what a straight line is, and you learned in Math 1C that we are able to find an equation representing a straight line. Okay. So do you remember an equation for a straight line is in principle an equation of this form: y equals to k value times x plus m. You remember something like that? So that is an equation for a line. What is the slope here is k. In British books they call it the gradient, yes? Gradient. Or of course in American books they call it the slope, okay. So k is the gradient, and that's the measure how inclined your line is, yes? If you have two lines, the slope of one is larger than the slope of the other one, it means that it is steeper, yes? So that's something like that. So the slope is a measure of how steep is your line, yes? And then what is the name for m, do you remember? Yes?
Is it y-intercept?
It's y-intercept. Yeah, it's y-intercept. Yes, so that is where your line actually intersects with the x-axis, with the y-axis, sorry. So if you have this one, for example, if you have this line, and then this point is the point whose x-coordinate is clearly 0, but its y-coordinate is m. And m is this number, and this is y equals to kx plus m, for example. Okay, by the way, do you remember if I have a horizontal line, what will be the slope?
0.
0. So it's good to remember these things. So if a horizontal line, the slope is 0. If you have a line inclined in this direction, of course the exact value depends how steep the line is, but it is definitely a positive slope. And if you have a line of this type inclined in that direction, it is a negative slope. But there is a deficiency with this form. We also discussed about that in Math 2C, I think. What the deficiency of that equation for a line is? You remember? So if I start changing k value and m value, what will happen? If I keep k constant and change m, the line will go up or down, yes, depending on how the value of m is. But if I keep m the same, for example, and I start changing k, the line will start rotating because the slope will change. So all the lines that you are interested in, mainly, you can find them from this formula by changing k, by choosing appropriate values for k and m, unless one category of lines, yes? The vertical lines. The vertical lines, the equation for a vertical line, if I ask you y equals to 2x plus 5, if I ask you what is the k value, you immediately answer k value is 2. What is the m value is 5. So it means if I ask you, I don't know, this equation, minus 3 over 2x minus the square root of 5, again, that's also okay. The k value here is minus 3 halves, and the m value is minus the square root of 5. But if I ask you what is an equation for this line, assume that this 1 and 2, this is point 2 on the x-axis, and then I can draw a vertical line, yes? I can draw a vertical line here. You remember what the equation of this vertical line is? What does it mean, by the way, of an equation? So it means that what is the general property of the points on this line? Yes? What do they share in common? Yes? Abdul?
They have the same x value.
The same x value, and that is exactly equal to?
2.
2. So what is an equation for this line?
X equals to 2.
X equals to 2 is a good representation for this line. And if I ask you, can you fine-tune k and m in this equation so that I can get x equals to 2 back? The answer is no. Yes? Because you see here, the coefficients that I have, the numbers that I can play with are k and m, so I cannot get rid of y. But in order to generate x equals to 2, I should be able to get rid of y. But there is no choice for me for k and m so that it gives rise. So you see, this is an equation for any straight line except vertical lines. Yes? So vertical lines, you cannot draw them like that. But then we had a formula, we have a general form, if you remember. We had an equation of this form, ax plus by plus c equals to 0. That's also good to know. That is, in Math 2C, we called it the general form of an equation of a line. And in this case, we can also generate x equals to 2. Yes? For example, here, I choose a equals to 1, I choose b equal to 0, and I choose c equals to minus 2. And if I put these numbers here, then it becomes x, this becomes 0, and this becomes minus 2 equals to 0. But if I move 2 to the right, it exactly generates that formula for me. So this is, for our lesson, it's good to know about vertical lines, but in the future we will not work with these that much. So what matters for us are non-vertical lines, and if I have a non-vertical line, this formula is quite okay for me. Yes? Is that clear? Okay. And if I ask you, what is the slope of this vertical line? What's the slope? Is
0.
not defined. No, 0 is for horizontal lines. So it's not defined. That's also good to know. If I ask you what is the formula for finding the k value, do you remember? It is y2 minus y1 divided by x2 minus x1. If I ask you what are these four numbers, you would say that x1 and y1 are the coordinates of one point on the line, and x2 and y2 are the coordinates of another point on the line. If I give you the points, 2 points on the line, you can put them in this formula and find the slope. Yes? And you see that this formula does not work if x1 and x2 are the same, because the denominator vanishes. And that happens exactly for vertical lines. Yes? If I have a vertical line here, what is the x coordinate? Is 2, y coordinate is something, it depends to this length, whatever it is. And for example, let me choose this one. Again, what is the x coordinate? Is 2, and the y coordinate doesn't matter. If I choose, so let me write it y2, and let me call it y1. But if I want to put these numbers into these formulas, y2 minus y1, I don't have any problems with. But in the denominator, I will have 2 minus 2, which is 0, which is not defined. So remember, horizontal lines, k is 0, positive slope, negative slope, undefined slope. Is that understandable? That is what we have learned actually in Math 2. See, I'm just reviewing things. Okay. So there are two standard problems. I want to refresh your memory about that, and then let me write the problems here. So I really want you to learn. This is just what we need in this course from Math 2C. So determine an equation for the straight line, in this course, when I say line, I always mean a straight line. For the straight line, whose slope is, for example, -3, and it passes through the point, say for example a, -2 and -4. So this is one standard problem in Math 2C. I give you two pieces of information about a straight line. I give you the slope directly, and I give you one point as a representative point on the straight line, and I ask you find an equation for it. And I want to solve it in two different ways. Both of them we studied in Math 2C, and I will preferably in Math 3C always use the second method. Okay? So method 1, method 2. So I would say preferable. Okay, so in method 1, I would say that, okay, you have given me a slope, so I know that this is not a vertical line because you have given me the slope, otherwise the slope is not defined. So I am on the safe side if I say that an equation that I am looking for is of this type. And then you have given me k value directly, so what I do, I replace k with that given value, and then m is still left for me, and this is why they have provided me an extra piece of information. My line is supposed to pass through that point. It means that the coordinates of that point will satisfy this equation. Yes, I will take y away and put -4. I will take x away and put -2, and then you see that the only thing which is left for me is m. So this becomes -4 is equal to 6, positive 6, plus m, and then I move 6 to the left, it becomes -10 equals to m. But what you have to provide as the answer, which is important, is to write y. Instead of k, I put -3x, and I just got that m is -10, yes? For method 2, if you remember, we had a formula, which fortunately is in the formula sheet as well. So I will write the formula here for you. This is why I'm writing it with red. Y minus y node, or y0, is equal to the k value x minus x node. Okay, if you remember in Math 1C Origo book, they call it 1-point formula. I mainly use this method in Math 3C. Okay, so what I'm supposed to put, I need to put a number for y node, I need to put a number for k, I need to put one number for x node. Okay, and then y, what are x node and y node? They are the coordinates of any point that somehow you know is on your line. It's given here. So y node is -4. X minus x node is x minus -2, and the k value is also directly given to you in the problem to be -3. Yes? And then what happens? I simplify this. So it becomes x plus 4 is equal to -3x, x plus 2. And then you simplify y becomes -3x minus 6, and then I move 4 to the other side, it becomes -10. Of course you see that the answers are exactly the same, but let us use this formula more often. Any questions? And one more example I want to tell you here, and then immediately I want to go to the notion of the derivative, which changed actually the human history. Yes? So here, let me give you another example. Of course, this example is directly related to the notion of the derivative that I want to talk. But let me also remind you of this. Might be there are some examples in the book that you need to remember this. So this is really needed right now, this idea. But this one I'm just telling you for completeness. Okay. So example, what happens if I say you determine an equation for the straight line that passes through the points Okay, let me give two examples here. Part 1, 2 points, let me call them -1 and 3, and B -1 and 4. 2, A 2 and 3, B -3 and -5. The reason that I gave you two examples because I want to draw your attention to one simple point. So is the question clear? I give you 2 points and I'm asking you find an equation of the line passing through those 2 points. And that's always unique. If I give you 2 points, for example, here and there, and if I ask you what is the line passing through them, then of course you can take the ruler and put them here and that's the line, yes? And that's always unique. I cannot ask you what is the line passing through one single point, because there are infinitely many lines passing through that point, yes? But for 2 points, that's good. So, but you see here, if I want to solve that problem, again, what I need to know the slope, I need to know 1 point. Instead of 1 point, in each case, I have 2 points. So I do not have any problems with 1 point. I can choose this one or that one. But I need to find the slope. So if I want to do the slope, what is the slope of this line? So the formula for the slope, let me repeat it again here. So K value is y2 minus y1 divided by x2 minus x1. Or do you remember sometimes people write it delta y, delta x. They are the same thing. So what is the slope of the line that passes through 1, A and B in this case? Look at these numbers.
Undefined.
Undefined, yes? Because they have the same x coordinates. If I have the same x coordinates, when I put them in the denominator, the coordinates, the denominator becomes 0 as undefined. So that's a vertical line. So if that's a vertical line, I don't need to go through that process because this will not answer me. This is only for non-vertical lines. So, but this answer to this is very simple now. Can you tell me what the answer is? X equals to -1, as simple as that. So as soon as you see the x coordinates are the same, you really don't need to go to the process that I'm describing right now. You just write x equals to -1 is the answer to the problem. Yes? But when I go to the second one, I have to calculate. So what should I do? I take the k value, I would write y2 minus y1 divided by x2 minus x1. By the way, these are names. It doesn't matter if you write y1 minus y2, but if you do that, you have to write x1 minus x2 as well. And it doesn't matter which one you want to name x1 and x2, which one you want to name y1 and y2. So I would say that this is x1 and y1, for example, and then I will call this one x2 and y2. It doesn't matter if you name it the other way around. And then I put them into this equation. y2 is -5, a negative sign in the formula, and y1 is 3. x2 is -3, a negative sign in the formula, x1 is 2. You calculate that, it becomes -8 divided by -5. So if I simplify the negative signs, so it becomes 8 over 5. Okay, and then I can use 1-point formula. So I would write y minus y node equals to k x minus x node. I hope that you are not confused here. So y, if I ask you what is k, k is exactly this number, but if I ask you what is x node and y node, you would say that x node and y node in that formula refer to the coordinates of 1 point on the line. So x node and y node can be these two numbers if I like to, or they can be these two numbers if I like to, or any other numbers for the coordinates of any point on that one. So let us choose the positive ones, which are easier in this case. But if you choose this one, the intermediate step would be different, but the final simplified form would be the same. Yes? You can test it yourself. So this becomes y minus 3, k value is 8 over 5, and then I have x minus 2. Okay, if you want to, you can simplify that, so it becomes 8 over 5x. If I multiply this, I can do it in a scratch paper. I multiply 8 over 5 by 2, it becomes negative 16 over 5. And then I move 3 to the other side, it becomes positive. And then if I take the common denominator, it becomes minus 1 over 5. Okay, for the time being, we don't need this example that much, but that example is important. Okay, any questions? Okay, now let me just end this by one phrase. If I ask you to find an equation of a straight line, two pieces of information is actually necessary. One of them is the slope and the other one is a point on the line. Yes? As soon as you have the slope and you have the coordinates of one single point on the line, then you can use the 1-point formula, for example, to write an equation for the line. Okay, for the time being now, this is enough. Let me go back to the notion of the derivative. Okay. There were two contemporary mathematicians, or probably or physicists, in the 17th century. One of them from Germany called Leibniz, and the other one from Britain, Newton. Yes, they were thinking about apparently two completely different problems. Okay, I want to start with the one who Leibniz was thinking because it was a mathematics problem. So he was thinking that if you give me a function, let me just try to be a little bit careful in my drawings here. So assume that you have this y-axis, and then you have this as your x-axis. Okay, so let me make it a little bit longer here. Okay, so this is x-axis and this is y-axis. And this is, for example, the origin. So Leibniz is also a genius, actually, from Germany. So he was thinking in this problem. He wanted to solve this problem. He was thinking that, okay, if you give me a function and I'm able to draw the graph of the function, for example, you give me a function f of x. You give it to me. For example, f of x equals to x squared. I don't know, f of x equals to sine x, or whatever. Yes? So you give me a function. I draw the graph of the function, So let me just do that. For example, you can assume that this is the graph of your function, y equals to f of x. And then you give me a point on that graph. So for example, let us consider that here. You give me a point here on this graph. Assume that its x coordinate is a. Okay? So f of x is given. This number is also given. And corresponding to that number, you go up and find a point on your graph. And the question that Leibniz was asking is that if I draw a line which is tangent to this graph, how can I find an equation for that tangent line? That was the problem, yes? So all of us have some intuitive idea of what a tangent is. I want to rely on your intuition, of course, in this level. It's not a good line. Let me make it better. So here, hopefully this will work this time. So yes. So this is the line. I will call it the tangent line. So it just touches the graph. So I don't want to make it more precise because then it becomes a little bit mathematically hard, but intuitively you understand what is the meaning of the tangent line. That's the tangent line. So the point is that you give me the function, you give me this number, I want to find an equation for this red line. Is that clear? So that was the problem Leibniz was thinking. And by the way, this simple problem changes the human history. So whatever you have right now is highly related to this problem. Okay? Whatever you have, for example, electronics, so iPhone and everything that we're using is depending on this one, because it is the birth of actually the derivative, the notion of the derivative, which I'll explain how this becomes so important. But probably at that time, even he didn't know about the applications at that particular time, yes? So now tell me, forget about these blue parts. If I want to find an equation for this line according to the recap we just had, so what I'm supposed to do? I want to find an equation for this red line. There is one way for me to do that, yes? I need to know a point from that line. I need to know the slope of that line. Yes? The point I don't have any problems, yes? Because I told you that the function is given, the point A is given. So if I call this point T, there is the reason for I call it T, because there is a name for this T. It's called the point of tangency. Okay? The point of tangency. So this point is called the point of tangency. If I ask you, can you tell me the coordinates of this point? The x-coordinate of this point is, what is A? And then what will be the y-coordinate? Yes?
F of A.
F of A. Do you remember from some previous courses that is the function? So this point has two properties. It lies on the red line on the one hand. On the other hand, it lies on the curve as well. Yes? So this point is on the curve. So if I want to find its y-coordinate, I can put A into this function. What I get is the y-coordinate for that point. Is that understandable from what we had for functions? So the coordinates of A and f of A, this is a given number. A, I told you from the beginning, I give it to you. And f, I give it to you, so you put A instead of x and you just do some calculations. Whatever you get, A and f of A is given to you. Yes? And then let me go to the 1-point formula we learned today. If I want to write an equation for the red line, how should I do that? The formula today we learned is this one. Do you remember?
Yes.
Okay. So, can you tell me, in this equation, what should I write instead of x node? A, exactly. On the right, on the left-hand side, what should I write instead of y node?
F of X.
F of?
X.
F of A,
Oh.
not x.
Okay.
Yes? And then what is left for me to do? I am supposed to know this number. I am supposed to know this number. I know them. But I am also supposed to know this number, which I don't know yet. Yes, so the point is that this k is missing. So Leibniz also realized to complete this problem, there is only one problem for him left, and that is finding the value for k. Is that understandable? And he realized that he cannot use this formula directly, because he knew about the formula for k as well, but this is not applicable here. Why? So if I write k, how many points do I need? 2. But how many points do I have right now? 1. There is, of course, this is a diagram. This is based on that I have the red line. Of course, I can say this one, but if you ask me what are the coordinates, I don't know. So the only point that I know is the point of tangency if I give you f and if I give you a. So even though Leibniz knew about this formula, but he was not able to use this formula for finding k because he doesn't know any other points on the line. Yes? But he actually was a little bit clever, and he said that, okay, let me somehow use this, not exactly but approximately. Okay, so what does it mean? He said that, okay, let me move a little bit to the right. For example, h units. I move h units to the right. And then I get, for example, let me make it a little bit longer here. So I go from a h units to the right, then this number becomes what? A plus h. Yes? And then let me find another point on the graph. Be careful, this red line, you don't know it yet. I need to find another point on the graph. Yes? Okay, so let me call this point A for the time being. Okay, can you write the coordinates of A for me here? What is the x coordinate according to this figure? A plus h. Okay, everyone. What is the y coordinate? It means what is the y coordinate? What is this height now? Yes, Kaja?
A function of a plus h?
F of a plus h, if you mean this. Yes? Yes, exactly. So that is f of a plus h. So h, I know it myself because, for example, I move 1 centimeters. I can move 10 centimeters. So that is the value for h. So h is under my control. A is also given to me, and function is also given to me. So this is still, I know it. And then the point is that there is one minor point is left. If you just draw this line, this line here, this line, can I write an equation for this orange line in principle? What? This is yes, absolutely yes, yes, because the coordinates of the point T is known, the coordinates of the point A is also known, and then I can use the k-value formula to find the slope of this orange line and write an equation. Okay, so let us momentarily do that. So, you help me to do that. Okay, can you tell me what is the k-value of TA? By the way, do you think TA is a tangent line? Is it a good way to call TA tangent? No. This is called a secant line, yes? So TA is called a secant line, yes? So let us find the k-value for the secant line. This is possible. Yes, what I write y of point A minus y of point T divided by x of point A minus x of point T. Yes, so let us calculate this. So what is y of A? You see it here on the board. This value is y of A. So I replace it. So it becomes f of A plus h minus. What is the y value for T? You have it on the board. It is f of A divided by, what is x of A? x of a, you see it, it is a plus h, minus, what is x of t is just a. I can simplify it a little bit, so I can write k of the secant line is equal to f of a plus h minus f of a divided by, are you with me? H. So this is the k value of the secant line. But if Leibniz wants to sell this k value for the k value of the tangent line, probably you will not buy it because these are not the same lines, yes? This orange line was not my target. My target was to find an equation for the red line. And this one is the k value of this orange line. But he was clever. He said that why should I go so much to the right? I can go to the right a little bit smaller. Okay, so let us see. That's the notion of limit that is coming into the game, yes? So, instead of going that much, let me repeat the process again, but go a little bit smaller, okay? I will not, so here, from here to here is my h. Let me make h a little bit shorter, okay? So, then let me change my color here. Assume that instead of going from here to here, I go a little bit before that. I stop here. So let me consider that this is a plus h. So this new h is smaller than the previous h. And I want to repeat the process again. So what I do, I will do that. I hope that you agree with me. Instead of having this as my point A, this will now play the role of point A. Yes? And let me draw the secant line again. Of course, I am using the same letter, but these points are not the same as you see them, yes? Yes. So I will get this green line here. Still, the green line is a secant line, but it is closer to my target than the previous secant line. Is that understandable? So, if I ask you, what are the coordinates of this, again the same thing. A plus h, f of a plus h, but of course for a smaller h, not for the previous h. But, if you do the same calculation, you will get the same expression for the k value of this green line, which is still a secant line. Is that understandable? The whole point is this. The previous secant line is a poorer approximation than this green line to the real tangent line. So this was the point. If I make this one even smaller, what will happen? Then I will be probably here. So let me, I don't know how many, so let me use black here. So if I make it smaller, then this point will be somewhere here, yes? This point will be here. And then if I draw the secant line this time, yes, I have to be careful here. Anyway, hopefully you understand what I mean. So that would be the new point A. So if I ask you which one of these three lines is a better approximation to the red line, it is clear for this black one. So the black one corresponds to a smaller h or a bigger h? To a smaller h. Yes? So you see that in the beginning, h was from here to here, this long. And then the second one was this long. And the third one was this long. So when I am making h smaller and smaller, I am getting a better and better approximation to what I need. Yes? Ideally, what should be the value for h to reach my goal?
0.
0. But there is a big problem with 0. You see, h appears in the denominator and it cannot be equal to 0. That's unfortunate. So the ideal is to make h equal to 0, and then what happens is that this formula doesn't make sense. So Leibniz assumed that I can make h very, very small, but not equal to 0. There is one constraint. I should make it very small, but not equal to 0. And then the notation in mathematics we use for that, we say that h approaches to 0. Okay? H approaches to 0 means that h is very small but not equal to 0. That is the crucial part. Yes? Because if it becomes 0, I have big problems here. So this means that h is very, by the way, this is very hard topic if you want to do it advanced. So I have to put quotation marks here. What is the meaning of very here? Forget about that. We cannot talk about this at this level. H is very small, but this is crucial. H is not equal to 0. This is what we mean by this symbol. How we read it? We say that h tends to 0, or we can say h approaches to 0, or we can say h becomes close to 0. Yes? But approaches is the best probably word. Okay, so the point is that this is the intuitive way. I want to make this idea reasonable. I am not proving anything. I am making this thing that I want to write plausible. That's it. That's the point. So I want to write the k value that I am looking for, which was the k of tangent, yes, is equal to k of the secant line when h goes to 0, approaches to 0. I want to make this plausible. Is that understandable? It's completely intuitive at this level, yes? Is that understandable that this is a good way of explaining things according to this intuitive picture? And when I am making h smaller, what happens? H is this length, then it becomes this length, then it becomes this length, and you see that these secant lines are rotating about O. So you see that if I make it very, very close, it becomes very close to the tangent line. And when h becomes very, very negligible, but not 0, what I intuitively understand that k of the secant line in this limit becomes the k of the tangent line. That's just I want to motivate you to see that this is plausible to define. Yes? Yeah.
But it's not exactly the same.
No, there is no way to say it exactly. That's what I'm saying, that in principle, this is the definition of a tangent line. But now I am doing it the other way around. I am counting on your intuition about a tangent line and try to sell it the other way around.
Sure.
But to be honest, this is the meaning of the tangent line. So the line whose slope follows this is called the tangent line.
Okay.
Yes, but I am relying on your intuition about the tangent line from the tangent to a circle, and I am taking this for granted, this intuition, and I'm trying to make this formula plausible for you. But in principle, if you want to do it rigorously in mathematics, you should say that a line whose slope is defined in this way is called the tangent line. Yes, that would be a little bit more rigorous way. And of course, we don't write it like this. There is also another symbol, which was the last part of chapter 1. I will come back to it, and that is called the limit. So it means that if I want to read it intuitively, I would say that the k value for the tangent is the limiting value of the k of the secant on the condition that h goes to 0. It becomes very small. So that is the idea that people are interested in the notion of the limit in the first place. Why we are interested in studying limits is because of that. Yes, we want to study what will happen for a function when a variable approaches to a number, but it is not allowed to be equal to that number. Yes. So in principle, what Leibniz in the by the way, it takes I think 200 years for mathematicians to design a good definition to come up with a good definition for limits. I think it was just done in the beginning of the 19th century. So the limit process is just a little bit hard for you to understand, but intuitively it's very clear. So that was in today's language, the k value for tangent, Leibniz come up with this formula. But this is just theory. It's on paper. In practice, this problem is not mathematically solved unless we can calculate that limit. Yes? If we can, we are done. I think at this level it is very instructive, even though I haven't talked about calculating limits formally, but I just want to motivate you that this is not a hard task to do. Yes? Let me give you exactly the simplest possible example probably ever for a function and then try to find its tangent line. Yes? Using this unfamiliar formula for you yet. I agree with you that there is something mysterious a little bit about this, how we should manipulate this, but this is, you see that in practice it is very simple. And when I motivated you that the notion of limit is necessary, then I can teach you some tricks and techniques to calculate harder limits. But yes, but in the book they talked about limits first, and it's good, mathematically it's good, but you see that Leibniz didn't know about limits. The problem was to find this. He was guided to a concept of limit. So historically, the notion of limit is coming after the notion of derivative. But of course, when you want to teach it logically, it's better to teach the limits first and then teach the derivatives. But let us follow this. I think historically it is easier for you to grasp the motivation. You know, what is the motivation behind these things. Okay, let me don't talk that much. First of all, I want you to respect Leibniz, to memorize that, even though unfortunately this is in the formula sheet. Yes. Yes. So this is the birth. I will come back to this. Let me give you an example. Let me clean this picture. We don't need it anymore. So I want to show that even though this is a little bit unfamiliar for us, but this is in practice really possible. Okay? This is the whole point, because if this is just on paper and it doesn't work, it's useless. Yes? Even though it might be a nice idea. Okay, so let me give you this very nice and very simple example. I don't know which function, if I ask you give me the simplest possible function that these things can be implemented, which function do you choose? X2 is probably, because if I choose f of x equals to x, then it becomes a straight line. And the notion of tangent to a straight line doesn't make that much sense. Okay? So, and then if I want to increase the level of that a little bit, then x squared is probably the best option. Yes? So let us exactly start with that one. So I would say consider, let me write it in this way. Determine an equation for the straight line that is tangent to the graph of the function as you said, f of x equals to x squared. Okay, do you think that I can stop here? Why?
Give you the point.
I have to give you the point, because if you have a curve, yes, I can have a tangent line here, this would be this line, I can have the tangent line here, these are different lines. So I cannot just give you the curve and ask you to find an equation for the tangent line. There is no tangent line, yes, unless I give you the point. So tangent to the graph of the function at the point on the graph whose x-coordinate is, for example, say 2. At this stage, I want you to understand what I have written here is exactly the Leibniz problem. Do you appreciate that? That's exactly the Leibniz problem for which function? For f of x equals to x squared. Can you tell me what is playing the role of this little a in this setup?
X.
No, in this setup. A was what? Do you remember what was A? I cleaned this board. But A was the x-coordinate of the point of tangency. Do you remember or not?
So A is 2.
A is 2 in this problem, yes? So A is 2 in this problem. F of x is x squared in this problem. Okay? So, I can demonstrate it using GeoGebra later, but if I want to draw a rough picture here for you, so you know the graph of x squared, that's a parabola. So if I want to draw that, so 0, 0, 1, 1, and then of course, let me put 2 here. If I put 2 here, what will happen? It becomes 4. And I don't know. So this is the graph of the function, but it is symmetric. It goes something like that here as well. It should be precisely symmetric. And then what is my goal? My goal is to find, this is the point, and I want to draw the tangent line here. Let me make it small. Yes. So my question is to find the equation, an equation for this orange line. Yes. Using the Leibniz method that we just developed here. So that is the question. Is it clear from geometrical point of view? That is the way that you have to imagine. Okay. And if you want to calculate that, you need the coordinates of one of these points on this orange line. Which one is the best option here? This is the only option that you have, and that is the point of tangency. But can you tell me, what are the coordinates of the point of tangency? The x-coordinate is 2, which is this 2. And what is the y-coordinate? 4. How did I get it? I put 2 in the function, I got 4. So no problems here. Okay, so I need, by the way, I need 1 point formula. So 1 y minus y node is k of tangent, let me write tangent, t for tangent, okay, x minus x node. So I need to know this number, I need to know this number, I need to know this number. These two I know. X node is 2, y node is 4. Yes? So the only thing that is left for me is the hard part, is finding the k value for the tangent using the Leibniz method. Yes? Let us just do that. So kt, let me write the formula to respect the soul of Leibniz, okay? And remember that. F of a plus h minus f of a divided by h, h goes to 0. Or approaches to 0. For the time being, don't let this part distract you. Okay? So let me just copy and paste the limit h goes to 0. Oh, sorry. This is the general formula. Here, what is a? A is 2. So I replace a with 2. So this becomes the limit of f of 2 plus h minus f of 2 divided by h. H goes to 0, approaches to 0. Okay, don't be distracted by this part. Okay, for the h, I cannot simplify anything with the denominator, so let me copy and paste. You know, if I ask you what can I write instead of f of 2, you know. What is that? 4. And there is a negative sign behind that. And then, what is f of 2 plus h? Can you tell me? We also had these ideas when, what is f of 2 plus h? What is the meaning of f of x? F is an operation, is an operator, is like a machine, gets an input from you, gives you an output. So the input is called x. What is the output? The output is the input to power 2. Yes? That's the meaning that you have to interpret. So if I ask you, what is the input here, you would say 2. What is the output is 4 in this case. What is the input? Can you read it, please? What is the input?
2 plus h.
So what will be the output?
2 plus h squared.
To the power of 2. So this is the way that you have to interpret that. So if I can calculate what is on the board, then I am done. But the point is that, what should I do? One way to do it is this. Take your calculator, put, for example, make a setup for yourself. This is, by the way, important to understand. Take your calculator. You want to make h very small, but you are not allowed to make it 0. So let us start with 0.1. For example, it's a small number, close to 0. And then you put h here, and then use your calculator. I don't know what the value will be. If I, so let me see. 2h2 plus, so 4 plus, 4 is gone, 4h, and then I have h squared. So that would be. So I think if you do it correctly, it should be 4.1. Approximately. Yes? Take your calculator, put 0.1 here. I don't know, calculate, do 2.1 to power 2 minus 4 divided by 0.1. Can you confirm that? Did you calculate that? So it becomes that number. Hopefully I am right. And if you make it smaller, 0.01, and then put it again in this and calculate it, you will get 4.01. Yes? The reason that I can calculate it so quickly because I simplified it algebraically. Okay, I'm just putting that in that number. Don't worry. What I ask you to do is to put this number here without this and just calculate that. And then if I make it even smaller, then it becomes this number. Yes? So, but I am still making it smaller because I told you that h is supposed to get very, very, very close to 0. The only thing that you cannot do is to put it exactly equal to 0. So I can increase these zeros, any number that I want, but I'm not allowed to make it exactly 0. So then what is your intuition by these numbers? These numbers here, they are approaching to which number?
0.
To 0. But I hope that you have some intuition what these numbers are approaching to.
4.
It should be 4. So this is the meaning of limit. So it means that the limit of this function when h is very small is 4. It doesn't mean that it's exactly 4. It means that the limit value is 4. So it means that when I am making h very small, the value of my function is getting very close to 4. Okay? But of course this is by the way, this is the way Newton and Leibniz did it. Yes? Okay, at that time, this is the way that they did it. But now we want to do it a little bit better here. We want to calculate without using our calculators here. So instead of simply talking about this function, in the chapter 1 we learned how to work with rational functions. So we should be able to simplify this function using the tricks and techniques that we learned there, yes? So if I want to solve that problem, I will do it like this. I will continue. So don't be lazy, by the way. You have to copy and paste this limit part all the time until the very end. But don't let this distract you. Just try to simplify this as if you are simplifying a rational expression. By the way, this rational expression is much simpler than the ones that you practice for. So what should I do for simplification? I don't need to do anything with the denominator at all. So I need to simplify the numerator a little bit. So what should I do? Using a squaring pattern, expand that, see if something is simplified. So the first one to the power of 2 is 4. 2 times the first one times the second one. And the second one squared is what? H squared. And then I have a minus 4 at the end. And then I have H. Yes? And then what I do, I still can continue. So don't be lazy. Copy and paste this part all the time. The denominator is still H, but this 4 and that 4 are cancelled. I have 4H plus H squared. I told you, just copy and paste, but don't let this distract you. Can you simplify this one according to what you learned? The answer is yes, I have to factorize that. Am I allowed to simplify this H with that H? So every lesson you learn, it actually counts here. You're not allowed, you have to factorize the numerator. So copy and paste, don't forget. And then I take H out, it becomes 4 plus H, and then divided by H. Now, can I simplify this H with that H?
Yes.
Yes, but do you remember there was an obstacle in front of us when we wanted to simplify? I told you you have to be careful. Do you remember? If I simplify that, I am assuming that H is not 0. Do you remember? But in that topic, I told you that whenever we simplify, we are assuming that what we are simplifying is not 0. Yes? So, but here, what guarantees that H is not 0? This symbol.
Yes.
This symbol tells you that H goes to 0, very, very close to 0, but not 0. So I am on the safe side. I can simplify this H with that H with no problems. Yes? Then what happens, this becomes the limit of 4 plus H. H goes to 0. Goes to 0, it means approaches to 0. It gets close to 0. Okay, now if I ask you, can you tell me what would be the number that 4H will get close if I am making H negligible? 4. And that's exactly the answer that we intuitively got from the calculator. Yes? But this is the one that we want to learn. We want to learn how to do that. So limits, so Leibniz method actually worked. And the K value for the tangent is 4. Yes? Okay, so the K value for the tangent is 4. So let me clean this one now. So what we do, we say that the K value for the tangent is equal to what? 4. Okay. Okay, so now what I have to do, and then the point of tangency was 2 and 4. Yes? Now use the 1 point formula, or even if you want, you can use Kx plus M formula. It doesn't matter. But let me use 1 point formula. So what was the formula, do you remember? Y minus Y node is equal to the K value X minus X node. Yes? So it becomes Y. Okay, tell me, what should I replace? What should I put instead of Y node? 4. X node and Y node are coordinates of any point on the line, including the point of tangency. So I would write 4 for this. What do I write for K? For 4. What do I write for X node? 2. And then I simplify that. So it becomes Y minus 4 is equal to 4x minus 8. And I move this 4 to the other side. So Y becomes 4x minus 4. That's the answer. So that's an equation for the tangent line to the graph of that function. By the way, could you predict that the K value should be a positive value using the diagram that I drew in the beginning? Yes? Because if you remember, when I draw this parabola, that was the point, and I draw the tangent line in that way. Okay, any tangent line in that way is with the slope positive, yes, and that slope was positive. But we couldn't predict the exact value of the slope if we haven't done this calculation. So in this lesson, I wanted to motivate you that actually the limit process and whatever Leibniz was thinking is working. Yes, we were able to solve that problem at the end. Yes? Okay, so let me demonstrate it using GeoGebra as well for you. Just give me 1 second. Any questions here? Okay. Okay, so let us try to understand this using GeoGebra. So I go here and draw the graph of my function, which was, is it Swedish keyboard? No. Y equals to x squared, yes. So that is my function, yes. And now, what is the point of tangency? Do you remember it was x coordinate was 2, and then you realize that the y coordinate is 4, yes? Let me show that one to you. So here, this is my parabola, y equals to x squared, and then you have this x2, and then this becomes this point. So my goal is to draw a tangent line there and find its equation, yes?
Is there a relation between the value that y equals to 4 on the line, on the tangent, the points?
Repeat it,
Point
please.
T,
Yes.
coordinates 2, 4.
Yes.
There's a relation between y value 4 and the limit of a function.
No, that was a coincidence here.
Okay.
That's a good question. That was a coincidence that the value is the same as the y coordinate. That was a good question, thank you. But that is just a mere coincidence. Yes? Okay, so now here let me find that point. So I will take that point, and then I know that this would be the point of tangency. Yes? And then the good point is that GeoGebra has a special feature for drawing the tangent lines. So you go here, if I remember it correctly, well, yes, here, tangents. You click on it, and then what will happen, you go here, click on your curve, and then the point. Yes? And that is the tangent line. Let me change the color to make it more clear. And you still see it. I hope that this is being recorded. So a color, let me change it, for example, to red. Oops, this is okay, so that doesn't matter. I go back and do the tangent line once more. Hopefully this make it black this time. That's good. So that is this black line is actually the tangent line. Yes? And then GeoGebra is also capable of giving the equation, but it gives you an equation in the general form, not in this form. So, but we should be able to confirm that, by the way. So what I got is this one. So this I really don't understand why GeoGebra put it 0.5. I don't know the algorithm they are using, but let us confirm that this is why, by the way, I always say an equation, not the equation. Because this is one equation, this what I got is another equation. So you see there is no unique equation. This is why I don't use the equation. I have to use an equation. Okay? But I will not say a tangent line. I would say the tangent line at this point because that's unique. Okay, so let me try to confirm that what I got is actually the same equation here, or equivalent, not the same. Of course, you see that they are not the same. So y is equal to 4x minus 4. Let me move 4x to the left. So it becomes minus 4x, and then I have y here, and then I have minus 4 here. Agree? And then, to make this exactly like that, I want to make minus 4 to be equal to minus 2. So it motivates me to divide everything by 2. When I divide this by 2, it becomes minus 2x. What is the coefficient here? 1. When I divide it, it becomes 0.5y, and it becomes minus 2. I don't know why. This is a little bit of strange way, but so I mean that even if I want to write it in general form, I would prefer to write it in that form. But why GeoGebra has chosen to divide by 2, I don't know that. Okay, might be we can understand what's going on. But at least you see that this is the equation of the tangent line, and that is exactly what we got. And I think intuitively you agree with me. This is a good tangent line. Every one of us feel that. That is a tangent line. Yes?
Maybe the reason GeoGebra does it is because it's told to maybe use like the smallest number possible. Because you...
No, but even in that case, you can divide even more, yes?
Yeah, I guess.
Yeah, I don't know, but don't worry about that. But at least one GeoGebra gives us is exactly equivalent, even though not the same, equivalent to what I got. And it doesn't matter if you write this or that, they were correct. So is that clear? Yes or no? So here, of course, GeoGebra
Yes.
gives you the item that if you, by the way, you can answer your question here. You see, I am moving that point, that the points are different. So now can you tell me intuitively, without any calculations using Leibniz method, if I put this point on the origin, what would be an equation for the tangent line?
X equals to 0.
No?
Y equals
The
to 0.
y equals to 0. Yes? Because x-axis means y is equal to 0. Yes? So it is intuitively clear. For this particular problem, you really don't need to use Leibniz method because it is so intuitively clear. But, by the way, this is the bad way that GeoGebra is solving it. So you see this one is negative. If I move it to the right side, the coefficient of x becomes positive. So the k value is still positive. Yes, you see the k value is positive. And then if I continue moving it, you see the k value is still positive. And when I reach to here, it becomes exactly 0, but yes. And then if I go the other way around, you should expect that the k value is negative. Yes. And then it confirms that, because if I want to find the k value, I have to move this to the other side and then divide by 0. But if I move this one to the other side, it becomes negative. So these intuitive things I really want you to understand, because it will help you to solve a lot of problems if you have a good understanding of what's going on. Is that understandable? Yes or no?
Yes. Yeah.
Okay. I would think that let me for the time being at least pause the video. So let me also.
Well, look, you can talk about mathematicians that you like.
Okay. So let me tell you something more to finalize today's lesson. Now let us go back to Newton. Newton was solving a completely different problem. He was working on finding instantaneous velocity of a moving particle. Yes. So the one that is shown by your speed, the speedometer of the car, but there is a big difference between the speedometer and the velocity. Velocity includes the direction as well. Yes, so you can say that my velocity is minus 2 meters per second. It means that I am moving with 2 meters per second in the opposite of the conventional direction that you have chosen for the positive one. But for the time being, forget about velocity. Let us talk about the speed, but the instantaneous one. That is also important. So you see, Newton actually was thinking to solve another problem. So he was thinking that I have a moving particle. Let us keep the one dimension. For example, assume that your particle here is moving on the x direction. And then you choose an origin for here. At time t, at times say t, your particle is here. The distance, let us consider it s of t. The distance from my particle to the origin at time t is denoted by s of t. That's also a function, yes? Why? Because when my particle starts moving, this value will change, yes? Its distance to the origin will change. So what does it mean? It means that the distance of my particle to the origin is a function of time. Is that understandable? Is this phrase understandable? Yes? It changes by time. Now, he wanted to find a formula. So using that formula, he wanted to calculate the speed, instantaneous speed of that particle. Okay? He didn't know how to do it, but he was able to do the average speed. Yes? So he said to himself, even though I don't know the exact value for the speed at this moment, but if I wait h seconds, the time will be what? T plus h. And the distance of my particle to the origin becomes s of t plus h. Then I know how to calculate this distance. What is this distance now? From here to here is st plus h. From here to here is st. If I subtract them, I hope that you agree this quantity is exactly this length. Yes or no?
Yes.
Okay. So this is the distance traveled by moving particle. How much time has passed? H seconds. So I divide it by h, and what I get is the average velocity. Let me write this bar for average velocity. So Newton realized that this is the formula. Of course, everyone at that time knew about that. This is the formula for the average velocity. Yes? When the particle starts at time t and ends at 8 seconds later. Is that understandable? So that is the average velocity. But he didn't want to find the average velocity. He wanted to find the reading on the speedometer exactly at that time. Yes? Is that clear? So he said to himself, how should I do that? You see, the same process will start in his head. He said that instead of waiting 8 seconds, let me make 8 shorter. Let me stay a little bit shorter. Then what will happen? You will get exactly the average velocity again, but for a shorter interval. Yes? And now let me make it even shorter. I will get an average velocity for even shorter interval. Yes? Then, because we are living in this universe and we have some intuitive ideas how things work in this universe, we know that if I do not give enough time to my particle, the change in speed will not be substantial. Yes? Of course, if this particle is moving very fast, like the photon in a light, even if I give 1 second chance to a photon, it travels 3,100 kilometers, yes? Yes. Or 300,000 kilometers. But if I don't give the photon even that chance, if I give it 10 to the power of minus 100 seconds, even the photon with a speed of 3 times 10 to the power of 8 meters per second cannot move that much. Yes? So it means that if I make this time interval shorter and shorter and still calculate the average velocity for shorter intervals, this average velocity will become very close to the instantaneous speed at that moment. So Newton realized to calculate the instantaneous, let me write INS for instantaneous, velocity is the average velocity, but when h becomes very small. And then you see this is very similar to what Leibniz did for a completely different setup. Is that understandable for everyone? So the V instantaneous is the average velocity, but if the time interval is very short. And now let me write this and then you can judge for yourself. So V instantaneous at time t is equal to this average velocity, st plus h minus st divided by h, limit h goes to 0. I think all of you agree with me that this is very similar to the Leibniz formula for the k value. Is that clear? So the only difference is that if I want to write the Leibniz formula, we had it like this. Yes? But you see, the structure and the structures are exactly similar. What's happening? Instead of function f, I have function s. Yes, in Swedish, the distance, you call it s or something. Yes? And then, instead of a, I have t here, because t is a better name in this setup, because t is supposed to represent time. But the structure is exactly the same. Do you see that? And then this was coming from a just mathematical curiosity. And this is coming from something practical in our universe. Yes, we are going to measure the instantaneous speed. So this is happening here. This structure also happens here. When something like this happens, mathematicians or physicists become excited. The reason is that it shows that there is a deeper reality to what we are doing. Because it was completely two different problems, apparently. But if you want to solve this problem, you need to do this. To the previous problem, you need to do this. If you want to solve this, you need to do a similar process. So it means that there is a deeper meaning to this limit. Yes? Is that understandable? And then, because this limit becomes important by these two examples and hundreds of examples that we can name them, mathematicians give this a name. And this is the way mathematics works. When something becomes important, it deserves a name and it deserves a symbol so that you can practice and learn more about that. Mathematicians decided to call this the derivative. Yes? They call this limit the derivative of f at a, and then they use this symbol to denote it, f prime of a. And the same thing here, but this time it becomes s prime of t. So let me just give you 2 or 3 minutes more and then we are done. So here today I started from 2 different setups and I just gave you, hopefully I could teach you in this way that this limit appears in this setup as well as the previous setup. They are completely different setups, but they give rise to the same concept. When something like this happens, and more examples actually will give rise to the same kind of limit, it turns out that this limit in its own is really important. So let us study this limit and extract as much as information from this as we can. And that is why mathematicians give this a name, and that is called the derivative, and then they give it a symbol so that they can call it or denote it. Okay? So this is the notion of the derivative. So that is more or less a very long introduction for what we want to know about the derivatives. But that is really important. Next time we will be more specific and solving some other problems and motivate. But I just want to tell you, from now on to Math 4, we are dealing with derivatives. Derivatives and integrals, of course.
And nothing else.
A little bit of trigonometry, but except for that, no. These are the only ones.
This is our life now.
Yes, this is your life. You get used to it, yes. And the point is that, unfortunately, you have to remember all of them for Math 4. So you need to find a way to study in a way that even in the summer you don't forget when I start Math 4, yes? Of course, Math 4 is not compulsory for you, but if you are taking that, I just want you to know that this is something that you have to know. Thank you very much.
Thank you.